Okay, welcome back to the class. Today we are going to learn about ensemble methods. So up until now, we have learned a lot of machine learning algorithm. Yeah, yeah, I'm already taking recording. So up until now, we learned many machine learning algorithm, and most of them um, will produce uh, one type of classifier. So basically, your algorithm will output one set of parameter, and then you use that one set of parameter to um, to perform the prediction on any data. So for today, we want to explore the possibility of combining multiple model, right? So to combine a multiple model, it's not just simply just like you add them or uh, you just basically take one, take many of them, and then you just add the result, right? So there has to be some way of combining so that you would achieve a more accurate uh, prediction. So we want to get a more accurate, right? So what does it mean? It means that when you have just one classifier, perhaps that classifier is very weak, right? It cannot achieve a high accuracy. But perhaps if you create a multiple single classifier and you can try a way to combine them, perhaps there is a way to improve accuracy, right? So I put more accurate in parentheses, and the reason being that is not always the case. There are some constraints, there are some conditions that you have to meet in order to achieve a higher accuracy than just a single classifier. This method collectively being called ensemble learning, right? So ensemble means gather together. So we want to have multiple classifier gather together and um, work on a task in conjunction of each other. So how can we combine many classifier, right? So this assemble method actually come into attention when there was a Netflix price challenge, right? So basically, Netflix published a database, right, about movie recommendation, um, about this user watch this movie, what are the likelihood that he will watch another movie, right? And this data set, they have a competition, and there's a group of researcher in 2009. They come up with a way of combining uh, multiple classifier and name them the ensemble method. And the improvement that they made actually make the top one in the leaderboard. So up until that time, um, people just think that just combining them doesn't actually contribute much um, to the classifier because like a single classifier should probably be good enough, right? So what make good ensemble? How to make a good use of many tools that you have, right? First of all, we want a member, basically one classifier inside, to be accurate. And we say accurate here, basically it has to be greater than chance, right? So what do I mean by greater than chance? If you have a binary, right? We have a binary classification. If you guess randomly, how many you get right, how many you get wrong? You get about half, right? 50%, right? If you just guess randomly. So they want the classifier inside to have something that is greater than chance. So this is the error rate, right? They want the error rate to be less than 50%, right? So this is for binary. If you have like multiple class, you can have a higher error rate. But in general, you have two classes, you want the error to be less than 50%. So this is for a single classifier. And another condition that we have to meet is that we want each classifier to be diverse. So what do I mean by diverse? Diverse mean they make a different error based on the same data. So different error doesn't necessarily mean that you guess everything differently, right? But even if they guess uh, the same prediction correct, the confidence of each classifier should be somewhat different. So we don't want them to agree on everything. And there's a good reason for that. Because we want to combine, right, many people with like different idea, right? So if everyone agree on the same idea, there's no point of combining them. You just use one, right? Because um, if one person make this decision, the rest should make the same decision. So there's no point in combining them. So we want a decision to be different between each of the classifier. So based on these two conditions, right, it's basically that we don't want a near perfect member. We only want it to be a little bit above above uh above chances, but it doesn't have to have a high accuracy. But collectively, they should be different, right? Because if one classifier is very accurate, there's no point in getting more classifier to make a group. So that are the two main points for Ensemble to be good. So when we talk about diversity in classifier, right? We want them to predict something different, right? If three classifier predict the same thing, then H1 will make a mistake. If uh, H1 make a mistake, then the other will also make a mistake. But if they have different opinion, they predict the same data point differently, there are higher chance that most of them will predict correctly. And collectively, if we can maybe do like a majority vote, right? We have like three classes, one vote for yes, one vote for no, and you take the majority vote. There's a good chance that the overall prediction will still be correct. So that is our hope, right? We hope that if we want to combine them, each of them should have a different opinion, but collectively, right, they should make the correct decision. Right. So this is the example. We have five, right? We have five classifier. This is the ground truth, right? And then these are everyone's prediction, right? So you can see that we have different prediction for every classifier, right? And if we take the majority vote, we still got the correct answer. right? If we take the answer from this 5 for this particular data set, you have number 2 to get it incorrectly, but the rest still got the correct answer. So if we do the majority vote, you will still get the same answer. Another thing to notice is about diversity. So if you look at number 3 and number 4, right, we have to look at number 3 and number 4. There is only one example that they differ in opinion. In this case, we can say that 3 and 4 are not very diverse, but because we only have like a small set of example, that like one of example would still contribute to about like 10% of the entire data set. So that is our like ideal scenario, right? We have the data set, we want to make many classifier. Each of them doesn't have to be perfect, but when we combine them, they give us a better result. So for ensemble method to achieve a higher accuracy, we can think of it as a statistical problem, right? So we have a limited number of training data. So we also have a many number of hypotheses, right? So hypothesis is can be like classifier in our case, right? So we have a lot of hypotheses that can explain the data, and each one of them would explain the data differently, right? Because we look at a different hypothesis. And if we only have to pick one hypothesis, right? So we have this hypothesis space like H here. So I just draw just like an enclosed space, but this is the space of hypothesis, right? And then when you do some training, like your one classifier is gonna be in one of these dots, right? You're gonna pick one classifier. You're gonna pick one hypothesis, and the chance that you will pick the perfect hypothesis is very low because the space for the hypothesis is almost infinite. So if you can only pick one, you are most likely not gonna pick the perfect one. But if you use ensemble method, you have more chances because you create multiple classifiers. So there are more chances that one of them could be like a perfect hypothesis. If you have a lot of data, there is also a problem with local minima, right? So in our hypothesis space, right, if we use gradient descent, it's gonna go to the direction that we have the highest gradient, right? However, if the space is not like smooth, it's not concave, or it's not convex, then you would stuck in a local minima. And if you pick one, maybe each one of them will stuck to its own local minima and never reach the perfect hypothesis. But if we pick multiple one and then we combine them, maybe we don't need a perfect hypothesis. We need many hypotheses that are good enough. And hopefully, if they join hand, perhaps they would get a better result. So the ensemble can solve a nonlinear problem. So up until now, when we learn about classifying method, right, we actually split between linear and non-linear, right? So we think that okay, if for for the data that's linearly separable, we should use like a linear classifier. If it's not, then we will use a non-linear. But for ensemble method, the base model, right, the member of the ensemble doesn't have to be non-linear. Like all of them can be linear, but when you combine them, it can form a non-linear surface. So the ensemble of linear classifier can have a non-linear decision boundary. Right? This is very similar when we learn about the k nearest neighbor, right? So when we have a lot of neighbor, you can draw the decision boundary, and this one you can use linear classifier because for the linear classifier it's faster to train and it's easier to explain, and then you can still get the nonlinear decision boundary without using kernel. Well, in a sense, Ensemble is your kernel, but it's not a typical kernel that you put on the data, right? You already got the classifier, and then you want to combine them. So that are the reason why the Ensemble method is very strong. So how do we make an ensemble, right? The easy part is, well, we have learned a lot of linear classifiers, so we can use them. The hard part is how to make them diverse, right? Because if we train linear classifier multiple round with the same data, most likely you get the same classifier, right? So if you have the same classifier, there's no point in combining them. So we need a way to trick the classifier to make a different decision, right? So that's why we have to have some strategy, right? We need some strategy. So in general, our fx is our like ultimate function. So this is the output function for our ensemble, and then we have this small h. This small h is a member of the classifier, and each member will also be given a weight, right? So not everyone have a share vote. Some of them would have a higher like score when they make a prediction, and then we can combine all the prediction together, and then we get the result. So how do we obtain a diverse member, right? We want this HI to be different for every I, right? You pick maybe 10 classifier, you want all 10 classifier to be different. And the way that we make them different, there are three main paths that you can pick. The first one is by manipulating the training example, right? Because we have training example, perhaps if we train them with different example, right, there are more chance that they will be different. Um, we can also manipulate the input features because our data would have a lot of features, right? So maybe we just pick some, right? You pick some of them for this classifier, and then the other would be for another classifier. You can also manipulating the output target, right? This um, useful for when you have multiple class, right? Because in general, when you have multiple class, it is harder for the classifier to predict compared to having just two classes. So we will look at this all these paths, all these three paths in detail in this class. So let's start with manipulating the training example. So when you're manipulating the training example, you run the learning algorithm multiple times, and each time it will be on a different subset of training example, right? So perhaps you have uh like 1,000 example. You break them into a set of 100, and then you use this 100 to test each to train each classifier, right? So you have different classifier for each of the smaller data set. So this will generate multiple hypotheses, but there's no guarantee that all of them will be diverse, right? It will be heavily depend on the data, right? If you sample the data very good, right? This 100 can represent 1,000, then you still get the same result, right? So this method require the classifier to be unstable. And what do we mean by unstable? Unstable means that if you change the input very slightly, it will impact the classifier by a lot. So classifier that are really sensitive to outlier, that will be like unstable. And we have learned the unstable algorithm. We learn decision tree. We also learn neural network. So these two are one of the unstable algorithm. So if you want to manipulate the training example, those are your top two choices. For stable algorithm, like for example, like regression, nearest neighbor, or SVM, these are very robust to outlier. So even if you split the data into smaller groups, they would still give the similar result. So we would want these two, right? Decision tree or neural network. So I said that I split the data into smaller group. That is the simplest way to manipulate the training example. There are more strategic ways of manipulating the training example. One of them is called backing, um, stands for bootstrap aggregation. So this will sample, right, m example from the training set randomly with replacement. So what do I mean by replacement? Replacement means that when you, let's say you have 1,000 and then you take 100 and 100, right, two times, right, m equal to 100. When you sample two times, there are chances that the data in each two set are the same, right? So with replacement, you can still pick the example that the previous group already picked. So basically, it's just like you pick from the original every time. You never leave out after it's being picked. And then you train the classifier on the bootstrap replicate. So basically, train on this guy. And then you combine the classifier on using identical weight, right? So we say that each classifier would have a different weight. If we use backing, um, most of the time everyone will have the same importance. So when you combine them, you just summing them up, right? So this is called backing, right? So these are the diagram, right? You start from the data set, and then you create a smaller training set, and this training set can share examples, and then you have multiple decision tree, and then you have a way to combine the decision, and then you have the final result. Right? So that is the overview of the backing. And then, so we have backing for a while until 1995. We have something called Anaboost, and I think many of you may have heard of the word Anaboost. This is called adaptive boosting, and instead of sampling, right? So in backing, we just sample, we just pick at random, right? But here we will use training example to reweight, right? To reweight. So what does it mean by reweight, right? You want to put more weight on difficult example, right? So basically, you sample the first set, right? You take the classifier, and that classifier will be used to evaluate the entire data set. And whatever the one that the first classifier get wrong, you have more weight on those example. And when you create the second training set, you will sample based on the weight, right? So the example that I got wrong will be more likely to be picked in the next set, right? And then when you have the second set, then you do the same for the third set, the fourth set. And then when you combine the classifier, now we have a weight. Now this weight will be based on the accuracy on the weighted training set. Right? So if you have the classifier with a high accuracy on the weighted training set, this alpha will have a higher value. So in other boost term, we have HI. We will call it a weak learner or maybe a base learner. Um, so the word like classifier, learner or hypothesis are the same in our context. So when HI being weak learner, we want the HI to be very lightweight, right? They should have a small number of parameter so that it's weak but stronger than chances. And one way to make a classifier weak, right? So in decision tree, we can manipulate the weakness by limiting the number of depths, right? So if you use the full decision tree algorithm, it can create a really long chain of decision node, right? But if you want to make a decision tree weak, you can say let's say depth equal to 1, right? Depth equal to 1. So it's gonna make just two layer. And it will not cover the entire example space, but it still should be good enough than just a random chance. So let's look at the example. So we have the data in 2D. We have a positive example, we have a negative example, right? So in the perfect world, if you were to draw a decision boundary, right, it's gonna be something like this, right? That it can separate positive example and negative example perfectly. But this decision boundary is non-linear, so it's gonna be very tough to compute this. So we want to start with a weak classifier. In our case, when we have the 2D example, we will use this decision tree with only one decision node. That will become drawing a vertical line or a horizontal line, right? So the weak learner, you would draw maybe something like this, and then you say, oh, this is a positive example, and then the rest will be negative example, right? Or you draw the horizontal line, and you say that, okay, above is positive, and then below is negative, right? So that is your weak example. So we start, let's say we pick this line, right? We pick H1, right? And we say the left of H1 is positive, the right of H1 is negative. What is the accuracy of this line? So we have 10 data set, right? How many does it get correct? So you get 7, right? 7 correct and then 3 wrong. So the one in the circle is wrong, right? Basically. So this one will get 0.3. And then we will assign the alpha to be 0.42 for this classifier. And we will look at later why we set the alpha like this. So our classifier is okay. It's not perfect, but at least it get us about 70% accuracy, which is better than chance. And because these 3 examples predict incorrectly, right? When you want to create the next classifier, these 3 will have a higher weight, right? Because these are considered difficult example, because the first classifier cannot predict correctly, so it must be difficult. So it have more weight. So after it have more weight, we can build the second example. So in the second hypothesis, right, perhaps we pick this line. And we pick this line. How many did we get incorrectly? So we pick this line, the left should be positive, the right should be negative. We actually got 3 wrong, right? But because these are examples that the first classifier already got correctly, the error rate is not 0.3. The error rate would be 0.21 because it have less weight now, right? So this one will have a higher weight, this one will have a smaller weight. So even if they got 3 incorrect, but each one of them have a lower weight, is lower than 1. So we have a lower error rate, right? So it's less than 0.3 because of reweighting from the previous iteration. And when we have these three that are incorrect, right, we would think that, okay, this three would be a difficult example for the second classifier. So we have to boost up, right? So we have to boost up the weight. And then this one become back to the same weight as before. But the one that are got correct both times will be very small, right? The weight of this will be very small because the first two example already got it correctly. So there's like, you don't have to care about them because someone already got it correctly. So we don't have to worry about it, right? And then we can maybe pick the horizontal line. Um, this time, it get three incorrect, but because these three example that it got incorrect already pretty correctly in the previous two classifiers, so the weight would be even less, right? It's going to be even less than 0.21, right? Because before we have 0.21 for three incorrect, but now we have three incorrect, but the weight is even smaller. So we get something that is smaller than 0.21, which is 0.14. So that is how Adabus create a classifier. So as you can see, Adabus is creating a classifier in sequence, right? If it is it backing, then you can do them in parallel, right? Because after you sample the data, each one of them is trained differently, so you can put it in like different computer and train it. For Adabus, you have to finish your first classifier because the result of the first classifier will dictate the weight on the next training example for the second classifier. And the final decision boundary, right? When you add the size, right? You add the weight for the first classifier, weight times the second classifier, the third to the classifier, you will get a decision boundary like this, right? So the decision will be non-linear, right? So even if each one of them is linear, when you combine them, you will get a non-linear boundary. So that is the idea for Adabus. This is the entire algorithm. So as you can see, we start with uniform weight, right? So you have n data point, each one of them will have 1 over n weight. So before we have 10 data point, right? So for the first classifier, if it get one incorrectly, it get 0.1, right? So you can sum it up. So you start with equal weight. And then you go to each iteration, right? Each iteration will introduce new classifier. So we learn the classifier, right? You learn one classifier, and then you compute the error rate, right? So the error rate will be the number, the example that it get incorrectly times the weight. So you start with 1 over n. Basically, it's just the number of incorrect prediction for the first round. And if this one, the error rate is greater than 0.5, you stop. Why? Why do we stop when the error rate is 0.5? It's greater than 0.5. What happens if the error rate is greater than 0.5? What kind of classifier will give that condition true? it's going to be really bad, right? If the error rate is greater than 50%, it means that it's worse than chances, right? And we talk about it when we list the condition for a good example, right? So the first one would be it has to be better than chances. So the error rate has to be less than or equal to 0.5. So when we reach to the point that the error rate is greater than 0.5, then there's no point in creating more, because if you cannot get better at this iteration, in the next iteration, it's not going to help. So that is to make sure that each one of them is better than choice, is better than chances. So what if it have the error that is less than 0.5? So we have this weight updating, right? So we have, first of all, we have to set the alpha, right? Is the weight for that classifier. And this weight for the classifier is set to be 1/2 times the log of 1 minus the error rate divided by the error rate. Right? So this will give you the contribution. So if the error rate is very close to 0, right, you have a higher value for the weight. And after you have the alpha for that classifier, we want to update the weight, right? So the weight is going to be the weight of the previous iteration times the exponent of the alpha, y, and hi. So this expression here, actually it's slide. So this expression right here, what is this? What is yi times htxi? What is this? So yi is the label, right? It's the y of the data. Is your label. What is ht? ht is the classifier at this iteration. And then when you put xi inside, this is the prediction. So this is the actual, right? And this is the prediction. What happens if we multiply actual and prediction? So the classifier will predict -1 and 1, right? We have two classes. One class is -1, another class is 1. So if this predict correctly, what is the size of the product? If HT predict correctly, the actual and the prediction would have the same size. And when you multiply the number of the same size, you get a positive number, right? So for the correct example, you get a positive number. For incorrect, you will get a negative number. And this one, right, you have e to the minus alpha times, let's say if you got it correct, times a positive number. And this is going to be like 1 over e to the alpha plus, right? Right, alpha plus. And this one is going to be less than 1. So when you predict correctly, you multiply this into the original weight, you multiply a number that is less than 1, right? This one will be less than 1. So when you multiply something that is less than 1, you get a smaller number, right? So if you predict this example correctly, your weight for the next iteration will go down. But if you multiply by a negative example, right? So e to the alpha negative. So you have two negative that will cancel out. So we have this to be greater than 1. So basically you multiply the previous weight by a number that is greater than 1. So your weight is going to go up, right? So you start with 1 over n, right? If you multiply by 1.1, right? It's going to be more than 1 over n. But if you multiply by 0.9, it's going to be less than 1 over n. Right? So these are the expression that will increase the weight or decrease the weight. The CT in the bottom is the normalization term. It's just to make sure that if you sum the weight of all the data point, you will get one back, right? So don't worry about CT too much. It's the normalization term, right? The most important is the denominator, right? So once you get all this reweighting finished, then you go back and then you start the next iteration to build the second classifier, third classifier, and so on. And the final result, right? You will take the sign of the combined prediction, right? So each one of them will predict plus or minus, right? And then you have the weight, right? The weight is alpha. So everyone get to vote plus or minus, but based on the weight, someone vote would be like more important than the other. So this is the Adabus algorithm. So I already explained this about if I get the correct and incorrect, right? So if I got it correctly, then you will multiply by a small number. If you get incorrectly, you will multiply by a large number, right? So that is basically how the reweighting works. What about alpha? How do we set alpha, right? So we have alpha to be set based on the 1 minus error rate. It's basically the accuracy of the model. And then I just happen to pick this function. I actually forgot why this function, but if you look at some of the error rate, right? If the error rate is 0.5, the alpha would be 0. So it's basically just the same as like dropping it, right? So because the error rate is not better than chances, so the weight would be to 0. If you have 0.4, you get the weight to be 0.2, and then if you go to like 0.1, which is like 90% accuracy, you will get a weight is more than 1. So you can get a weight more than 1. So basically, some classifier will get more than 1 vote, right, per se. So that is other boost. It's more sophisticated than the backing, because you have to take care of the weight. But it's an interesting concept. So the effect on between the error rate and the weight or the contribution is basically carved like a log curve, right? We use the log function, so it's going to be something like this. So the more error you make, the contribution will go down very fast, right? So that is about manipulating the training example, right? We split the training example for the backing. For the other boost, we put a weight on it. What about input features? So in the most simple way for manipulating input features, basically we pick a subset of features, right? And then we train each classifier individually, and then we can combine them through the majority vote. And the example would be if you want to detect a human face, right? Instead of detecting the entire human face, we can have a classifier for the nose, the classifier for the mouth, the classifier for the eyes. And if all of them agree that, okay, in this picture, you have eye, you have nose, you have mouth, there are more chances that there will be a face in that image. And this is used in the Viola-Jones face detection. This one of the classic face detection, right? So in the Viola-Jones face detection, they have they build a classifier. They build a set of a classifier for each of the face part, right? You have this one is for the eye, right? Basically, the eye should be darker than your cheek, right? The eye part should be darker than your cheek. For the nose, right? You have you usually have two set of eye, right? You have the left eye, and then you have your forehead, and then you have the right eye. So you have like dark and then bright and then dark. So they build a classifier based on this intuition, and it works quite well. So that is the input feature, right? There's not much into it. There are no like sophisticated algorithm. You just have to pick the feature that you want to classify. And then the last one would be manipulating the output target. So this one is more convenient when you have to classify multiple classes, right? For example, you have K classes, which is very large. Let's say you want to classify like 1,000 type of flowers per se, right? And this 1,000 is going to be very tough to have a classifier for, you know, that many type of example. So what we can do, right? We can reduce this K into smaller number. And the way that we do it, right? We partition K class into two subsets A and B. Right? So we can have like 1,000 classes, but we group the classes into two big groups. Right? One would be label 0, one would be label 1. And then we construct a new classifier using this new group AB, and then we call it, HL or whatever. And then we repeat the same process, right? We partition the two subsets with different combination. And then we can do it multiple times. You get multiple classification. And if you want to classify X, right, using the H1, we have to look at if H1 is 0, each card in AI receive a vote, right? If H1 equal to 1, each class in BI receive a vote. And then the prediction would be the class with the highest number of votes. So let's look at the example. In our example, right, we have 4 classes. Like we have 4 colors. We build 2 classifiers with different group, right? So in the first iteration, perhaps we group green and red together. This will form a group A, right? A group A. And then we have the blue and the black together to be a group B. And then we train this classifier based on 2 groups. So before we have 4 classes, but now we have 2 classes. So we can use binary classifier, right? And we love binary classifier because it's only 2 things, right? It's very simple. And then we can do different group, right? Perhaps we group green and blue together to make a group A. And then red and black together to a group B. And then you create another classifier based on this grouping. So each grouping of the training data, you get a different classifier. And once you have each classifier, we want to do a prediction, right? We want to do a prediction. So let's say we have H0 and HL, right? So H0, the group would be, so this one will classify, let's say group A would be red and blue, right? Group A would be red and blue. And for the HL, the group A would be red and black. Okay. Red and black is blue. So let's suppose we have a new example, right? We have a new example X. And H1 predict A, that this one belongs to a group A. And HL predict to a group B. What would be the final result? So when the first classifier predict group A, we have to look what are inside the group A, right? In the group A, we have red and blue. So H1 is going to vote for red and blue. Right? For HL, right, it predicts that X, the new X, should be in group B. So what are the color of group B? The group B have red and black, like for group B. So this is actually B, right? So because you have red and black, it's gonna vote for red and black. And after all the classifier vote, you can sum up the vote total. So you get 2 red, 1 blue, 0 green, and then 1 black. And you will conclude that this new example X should be in the red group. So that is how you manipulate the output. Right? You have multiple classes. You can group them into 2 classes, and then you make a multiple classifier based on different grouping. And then they can do the vote this way. We also have the gradient boost regression tree. So before we have the classifier, right? And then we want to combine a different classifier. What about regression, right? Can we combine multiple regression together? The answer is you can, but it's going to be a little bit more tricky, right? For example, you have the graph hood like this, but if you have one regression tree that look, the first one would be look like this in the latter case, there will be like some example that are not explained, right? And then you want to make a new one that that you try to cover all of this point, and then you want to make the third one to make up for whatever the second one got incorrect. So the prediction would add up the tree to get the final result. And the way that they do it, they would use the least square loss, and then they compute the residue. So what is the residue? So the residue is the difference between the actual one and then the prediction. So when you start with the first regression tree, right? When you start with the first regression tree, some data will be explained perfectly, some data will be not. And you can compute the residue, which is the difference between the actual and the prediction. And for the second one, for the second tree, you will fit the regression tree onto the residue, right? Instead of just fitting to the same data set, we fit the residue. So we want to find a regression that can explain the residue of the first regression. And then the third one is going to do the same. It's going to try to come up with a regression tree that can explain the residue of the second tree. So we try to combine by calculating the we have the least square, and then you want to find the classifier, right? You want to find a classifier that can explain the least square the best, right? And then you combine each weight, each classifier with a different weight. Right, so this is so yi is the residue, right? So it is the residue is the if you use the least square, you take the partial derivative of this function with respect to the fx, right? So basically you will get like 2 times that value. And then you combine them based on the residue. So that is the gradient boost method for regression tree. So in summary, the ensemble method are the method that you want to achieve high accuracy, but using the low end classifier, right? And then you want to combine the low end classifier together to make the collective effort better. We know the two main algorithms, like we have backing and boosting. This is for manipulating the training example. We can also manipulating the features, also manipulating the output if you have multiple class. So it's important that you should meet two conditions that I said at the beginning, that like one, it has to be better than chance, right? And then two, it has to be diverse, right? These are the two main takeaway if you want to use the ensemble method. So any questions so far? So for ensemble method, there are no like complicated formula or equation. It's just understand most of the concept. We are going to take a 10-minute break, and then we come back. We will look at some code for ensemble method and perhaps some of the neural network that we didn't do last time. So we be back at like 10:20. Okay. So welcome back. We are going to look at some code for the Ensemble method. So first of all, we need a data set. This time I'm going to generate 2D data set with multiple classes, so we can try different Ensemble method. So we can use the sklearn library to create a data set. Going to have the data set import. Oh no, it have to be from sklearn data set import. There should be a function called make classification. So this function will generate the data for you. So we're gonna have x and y equal to make classification. So it's gonna be a classification problem. You can specify the number of sample. Let's start with like 1,000 example. Number of feature, because we want to visualize. I will only use two features. Um, and then we pick the number of classes. So we have, let's say we have also two classes. And then to make the example more complex, we can pick the cluster. Gonna be n cluster per class. So if we have only have one cluster for one class, it's gonna be easily to find the linear separation. But if one class have multiple cluster across the input space, then linear classifier may not be able to get that. So let's try about five cluster per class, right? And then we can have the random state. Let me make it so that it's harder. So random state. So because it's gonna generate at random, so you can pick the same number. So we have the same result. And then we can plot, right? We want to plot the data set in the 2D space. So this one you're gonna use the matplotlib, and then based on the y, you put into the color. So if we generate the data set like this, it's gonna take a little bit of time to start the engine, and then we will have the result quickly afterwards. Uh, so we have to put the number of informative, number of redundant, number of repeat. So this sum has to be less than the number of total feature. So we pick the end feature to be 2. So we need to have these two, basically these three number, informative, redundant, repeat, to be greater than, uh, to be less than or equal to end features. So we have to add more parameter, right? So we need to have redundant. So let's say we set it to 0. It means that we don't have the number of points, and then we have the informative to be 2. I think the repeat already hit be 1. So that is the only thing that we have to add, right? So what is it? So the number of class times the number of cluster per class must be smaller than 2 times the informative. So the informative is 2, so I can only have 2 cluster per class, I think. Okay, right? So we kind of have like two cluster, right? We have cluster here, and then we have cluster here for purple, and then we have this cluster for yellow, and then this cluster for yellow, right? So you have like multiple cluster, and then we have this overlapping data. So that is will be our data set, right? So we have two class, and if you use the linear, you cannot separate them. So we have our data, right? So we got to use the ensemble method, right? So we want to use ensemble method. Um, so to use ensemble method, you have to specify the base model, basically the weak learner. So they will use the decision tree um, for weak learner. So we start off with um, using the ensemble library. So we have Adaboost classifier. So this Adaboost classifier is the one that we discussed in class. Basically, it will manipulate the training example. And then we have to also import the weak learner, like which the decision tree. So we'll have the decision tree classifier. So when we import these two library, we have to uh, specify the weak learner first. Okay, so we have weak learner. Um, this is going to be the decision tree classification, and then we can say the max depth to be equal to 1. So when we have two-dimensional data, the max depth equal to 1 is basically you draw the horizontal line or the vertical line. Right? That is the same example that we used in the lecture earlier. So this one has to be max depth to be equal to 1 so that it becomes weak learner. And then we can uh, have the model equal to the other boost, right? Other boost classifier, right? And then we have the base estimator. So you send in the weak learner, right? The example of the weak learner to the base estimator, especially to be the member of the ensemble. And then you specify the number of estimator, like the number of classifier that you want to use. Let's try to be 5. Let's try 5 first. Oops, this one has to be weak learner. And then we can train on the data set. So I will show you first the weak learner if we use the weak learner alone. So we have this model and then the learner. Uh, Base estimator. Oh, there's no keyword. What is the keyword for base estimator? Oh, just estimator. There's no base. Okay. Okay, so we have weak learner and then we have the model. So let's try okay, so we can do the split 10 test first. So we have the x test out of the way. And then we will try to use the only weak learner. Like we want to see what is the accuracy of just one classifier on this data set. So we can say uh, we have the weak learner dot fit exact trace, and then we do the prediction, the y predict equal to the weak learner dot predict x test, and then we print out the accuracy, right? Okay. So if we only use the weak learner, right? So we have 98% of accuracy with high. So that is the just one learner. So now we want to try multiple weak learner, right? Via ensemble method. So for this, we already have the ensemble method here, in which the model, right? So we can say model dot fit x train x y train, and then you do the y prediction on the x test, and then we also print the accuracy. So we have the about the same accuracy, right? So because we only have how many estimator do we use? We use 5 estimator, right? And then we have the same result. So perhaps for this type of data set, um, maybe we create a more interesting one with different random state. So if I don't use random state, it's going to generate a different data set every time. So maybe this one may be more challenge. So we create the weak learner and also the example. We split the test and train. And then for weak learner, we get 0.875. And then for ensemble method, we also get the same. So we get the same result. Maybe my code is wrong. It should have slightly better results. So maybe if I create a new one here and then only use the example. Okay, so I guess because of the weak learner is already very good. When you combine them, maybe perhaps um it's not improving because each one of them already have a high accuracy. So maybe we try. Is there maybe this will be harder, perhaps. 10 test and then weak learner. Oh, still 0.9%. So you can it's still linearly separable, right? And then you get the same one. Okay. Right. So the ensemble method doesn't always guarantee increase um in the classification. So maybe if I make the if I change the weak learner to be higher depth, would it help? So if we use two depths, ah, still the same result. Have like three depths. So just one classifier with depth three is slightly better than the ensemble with just depth one. So you can play around with um, how you combine the ensemble. Perhaps if I use like maybe more features, let's say increase to like 20 features, I should be able to increase the number of cluster to something like 20, but it still have two classes. No, maybe just one, 10. So I still can only get two. Okay. So this is the very hard example because like all the data set are on top of each other. Let's see how each of them do. I use speed 10 test and then we use only use maybe depth 3 for this one. Get 8.85. If we use ensemble, you get 8.45. Right. So it's not always the increase uh, for the ensemble method. So that is how to use ensemble method with decision tree. Let's try to use a neural network for the base class, right? We haven't used neural network last time. So we want to build, right? Build ensemble, right, using neural network. So in the sklearn, we have MLP classifier. So MLP stands for multi-layer perceptron, right? So it's basically the neural network. And the way that we create the MLP, right? So we have the neural network base, right? It's going to be MLP classifier, and then you can specify the hidden layer side, right? So we have the input layer, we have the output layer, and then the middle is called the hidden layer, right? So you can specify the hidden layer size. Now this hidden layer size will take can take multiple number if you have multiple layer in the hidden layer, right? So if you just say 100 and then comma, something like this, you're going to have one hidden layer with 100 perceptron, 100 neuron. If you type in like 100, 100, it means that you're going to have two layers and each layer will have 100, right? So you can change the number as well, right? You can have the first layer to be 50, the second layer to be 100, and then the third layer to be 50, right? So for us, we want to use just 100 um, perceptron because we want it to be not sophisticated because we still want it to be a weak learner. So we will have 100 hidden layer size, and then we uh, let's try to fit the base model first, right? Let's try to fit the base model first. So you're gonna get about 0.875, right? Which when you compare, is about between the decision tree with make step 3 and also the example method of the decision tree with make step 1. And then we build the ensemble, right? So we have the NN ensemble equal to the uh, so here we let's try to create the base again. So base equal to the this one. We use the same base, right? And then we have the model equal to the other boost. The estimator would be the base, and then we have 5 number of estimator. And then we fit the model, right? So we have model dot fit x trace, and then we make the prediction, and then bit the accuracy. So that's a support sample weight. So let's see. So perhaps it passed the other boost. Uh, I see. So it cannot use neural network inside, I guess. Yeah, because other boosts work by assigning weight to the sample. Uh, is expect the best estimator to be able to handle the sample size weight. Let's see. So unfortunately, for the NLP classifier, it treats the dataset with equal weight for all the data, and there is no parameter or algorithm that take care of uh, the weight on the example or the training example after the first type of classification. So we can only use like maybe SVC or logistic regression that support the sample weight. We only use decision tree, but we haven't used SVC or logistic regression. But generally for SVC and logistic regression, the algorithm is stable. It means that it may be very hard to get a diverse estimator, but we can try. Uh, Now we got okay, so we will have like this fail because uh does not support sample weight from other boosts. Okay. So what if we use SVC, right? We haven't used SVC for a while. So from a scalar dot linear, right? Import SVC. This is called SVC. This is linear. So use SVC for ensemble. Oh, it's SVM. Okay. Dot SVM import SVC. And then we have the weak learner to be the SVC, and then we turn on the probability. So it's not the hard assignment for the SVC, but it's the probability distribution. And then we have the other boost, and then we do the test and see the accuracy. Right. So this one we have the 0.465, right? So it's basically a lot worse than the previous two, right? Because uh, like SVM cannot separate this for sure, but also uh, it is stable, so you're not gonna get the different opinion, right? So if I use just the SVC, right? If I use the just the SVC and only use this, um, yeah, only one will. If you use only one, it's gonna get the high accuracy already. So when you combine them, uh, it's basically simply not good. So all in all, if you want to have like a better performance, and want to use Ensemble, the most common choice would be the decision tree. You would want to use the decision tree for for the weak learner. Okay. So that should cover most of the basic idea. We learned about MLP this time. Uh, you can actually like even then more than the hidden layer, you can specify more in the inside, right? For example, you can pick the activation function. In general, it's gonna use the rectify linear unit for the activation function, but you can try a different one. The solver, basically how they figure out the weight. Um, in general, it's gonna be Adam. I don't see people not use Adam, so just keep it at that. Another one that you can pick is the learning rate, right? So you have the learning rate uh, strategy. The default one is would be the constant learning rate. If you want to use um, different one, you can say adaptive. And when you say adaptive, right, you have to specify the power, right, and also the max iteration. So we have the initialize the initial value, right? Normally you would pick if you use adaptive, it's gonna go down over time. So you want to start by a higher value, like 0.01 is already high, and then you can have the power t, right, to be the the decay factor, right? So you can specify all these parameters for the neural network, right? So this one would get you 0.87 for the adaptive weight. If you use a constant, you're gonna get about the same result. So for the assignment, I think there will be assignment due today. Um, so if you want to use the MLP classifier, you can play around with this parameter as well. And next week, there will be our last assignment for next week. I'm still debating whether to do the reinforcement learning or semi-supervised learning. Because like each of them is have a very complex setup on Kaggle. So I will look into which one would be like the easier to set up. And then we will have like 2 or 3 more class before the final exam. So we are toward the end. Hopefully you will learn a lot of things from this class and can build on the knowledge that you have. If you have any question, you can contact me in the Micro Canvas or via the Microsoft Team chat. Not only on the class project, but if you have like project in general, you need a consultant, then you can also ask me as well. So that is for today. I will see you again next week. Next week is going to be semi-supervised learning. All right. So see you next week.